Bismillahirrahmanirrahim. In this video we will discuss the load characteristics of a DC shunt generator. Here you can see the two meters. One is configured as a voltmeter and one is configured as an ammeter. This is our DC machine. Can be configured as separately excited or a shunt machine. This is the shaft. This one is the tachometer. This meter is configured as an ammeter because we will be measuring currents of the field winding, load and the motor. This is the load unit. This is available in different form in the lab. You can have some bulb based load in some experiments. This meter is configured as a voltmeter. This one is configured as an ammeter. And this load can be varied with the help of this knob. We will be sliding this knob to change the resistance at the terminals of the armature. Load will be connected in parallel to the armature of the machine which is configured as the generator. This load is available in different form in the lab. This is the main power supply unit. We will be changing the voltage with the help of this one. This provides supply to the terminal board and terminal board converts that one into DC, and then that DC supply can be used to run the machine as a motor. The motor will be acting as a prime mover that will be providing the mechanical power to the generator, and then the generator will convert it into the electrical form. So when the motor gives the mechanical power, the armature rotates in the presence of the magnetic field and EMF is induced in the armature. Here are the two supplies. So first of all, we are going to configure the motor. We are going to use the supply of 300 volt 6 ampere and we are going to provide power to the armature of the DC motor first of all. So this is the first wire that has been connected. The second wire from the second terminal of your source will be connected to the second terminal of your armature. So here you can see we have given this supply to the meter as well because we want to measure the voltage and current at the armature of the motor. If you need this one in the experiment, you can connect the meters. Otherwise, you can skip. In some of the experiments, you don't need to measure the motor voltage and current. In some experiments, you need to measure. So, please look at the manual of the experiment and then configure accordingly, right? So over here, what we have done basically, we have connected the ammeter in series with the armature and we have given this supply to the armature winding. This will be acting as an ammeter and will be recording the armature current. Okay. And now we will connect this armature in parallel to the field winding. That can be connected like that at A2 with F2 or A1 with F1 or A2 with F1 and A1 with F2. So in all the cases it will be in parallel. Field winding will be in parallel to the armature. So we have configured it as a DC shunt motor and we have connected the ammeter in series with the DC machine and it is basically measuring the whole of the current, the armature current as well as the field current, the total current that is being supplied to your motor. Right, and now the voltmeter we are connecting in parallel to the armature and that is in parallel to the field, so it will measure the armature as well as the field voltage because they are in parallel. So armature voltage and the field voltage that will be same. Ammeter is measuring the total current because that current will be divided later on in two parts, armature current and the field current. Now, when you will increase the voltage at the machine terminal, you will observe that the current will be increasing and at the same time the speed of your machine will be increasing because that is directly proportional to the applied voltage. So with the help of this you will be increasing the voltage, and once you increase the voltage, more current will be drawn by your machine and the more faster it will be running. Okay, so you can control the voltage and the motor in this experiment with the help of your power supply unit by controlling the voltage applied to this DC machine and by controlling the current as well if you connect a variable resistance in series. Okay, so we will be only controlling the voltage and we will be adjusting our speed at a certain level. And if you observe the negative values, then you can swap the terminals to get the positive values of the current and the voltmeter. If the voltmeter shows the negative, just swap the terminals, and if the ammeter shows the negative current, you can swap the wires, and then the um, current will be positive, right? Because the direction of the current through the meter will get changed. So here you can see now it's positive and the voltage is positive as well, right? So the product of these two will give you the power that is being supplied to your DC machine, the input power of your DC motor. If you need to record that one, set up these meters. If you do not need to record these ones, you can skip these motors. And this is the tachometer, and it is reading the speed, calculating the speed of your machine. So it's a speedometer or the tachometer. And when you will increase the voltage, you will observe the change in the speed of the DC motor. This DC motor is acting as a prime mover. It is rotating the armature in the generator. And now if there will be a magnetic field, that will be a residual magnetic field, okay, or you can give it through the external source at the field terminal of your generator, and then there will be the induced EMF across the armature terminals. So now we are going to connect this load with the generator. Generator will give you the electrical output and that will be consumed. The electrical power will be consumed across the load. So first of all, you can see we are going to use an ammeter in series with the load because we want to measure the load current, and it is set at the 20 ampere scale. So from the load we have connected the ammeter, right, that is in series with the load. Just observe the connection from this load to the meter, and then from the meter common terminal we will go to the armature of the machine because the load is to be connected in parallel to the armature. And as we are going to make it as a shunt machine, so in the shunt the field winding will be in parallel to the armature, so all of them will be connected in parallel. Okay, so we have connected with the terminal A1, and now from the terminal A2 we will connect the second terminal of the load. So this ammeter is in series with the load, and this ammeter and the load that is connected in parallel to the armature, right? But ammeter is in series with the load, right? Okay, and it is set at the 20 ampere scale because our load current will be can be varied from 0 to 6 ampere as per the machine ratings. Okay, now we are going to connect the field winding in parallel to the armature winding because we want to configure it as a shunt generator, right? So you can connect A2 with F1 or A2 with F2, and similarly A1 with F2 or A1 with F1. So in all the cases these two windings will be in parallel. Okay, so now we want to measure the field current. So what we are going to do, from the field winding we are going into the ammeter that is configured as a milliampere meter that is in series with the field winding, and now from here we will complete the loop and we will connect field winding in parallel to the armature. So here you can see, so we have come to this one ammeter, and from here with the help of the second wire, now we will connect it with the terminal of the armature, right? This one, the field that is in series with the ammeter and then coming back to the armature. So now this meter will record the field current, and if you want to vary the field current, you can connect and you can connect a rheostat in series. With the help of that, you will be able to control the field current, and if you will be changing the field current, you will observe the change in the voltage. So if it is required, so you can connect a rheostat in series. Okay, so at the moment we will be just observing the field current. We do not want to control it, so that's why we are not going to connect the rheostat in series. So here you can see now 120 milliampere is there, and what's the load voltage? Let's turn on this meter. So if you turn on this meter, and the load current is 1.15 ampere and negative sign, you can swap the terminals to get it positive, and then as I have shown you earlier, you can change the knob of the load, so you slider load, and you can change the load current. Okay, so now you can set the positive current, and you can change the load by sliding this. So it's a slider that will be used to change the load. You also have the load in the form of bulbs in the lab. So sometimes you will be using that one. That is very simple to use. You will be just switching the bulbs in parallel with the help of the switches. Now we are connecting the voltmeter in parallel to the load because we want to record the load voltage. So we have connected one terminal of the load with the meter, now the second terminal, and make sure that it is at the voltage scale 200 volt because our machine rating is 160 volt. So after connecting the voltmeter, now we are going to turn on the setup. All the meters have been set, all the wires have been placed, and now if when we will turn on the supply will be given to this terminal board, that will be converted into DC form, that will be running our DC shunt motor, that will be rotating, that will be giving mechanical input to the generator, and then the generator will give you the induced EMF. And if you do not observe the induced EMF, swap the field terminals because we have discussed the voltage buildup phenomena of the shunt generator in the theory class, that some residual magnetic field is required, and the flux because of the current in the field winding should support that residual flux such that the net magnetic field increases and you get the more induced EMF across the armature terminals. So just observe this one, what you're getting around about one. Let's complete the loop, and now you can observe we are getting 123 volt across the load. Again it's negative. If you swap the terminals you can make it positive, right? So it doesn't matter, uh, but let's swap the terminals. Okay, so now this voltmeter will give you a positive volt. So you're getting the voltage, but if you do not get that one, swap the field terminals, right? Such that the current because of the armature voltage that is giving you a flux, and that flux must support the residual magnetic field in order to get more induced EMF at the armature terminals. Okay, so the product of these two is the input power because this is the current and this one is the voltage. So if you multiply these two, you are going to get the input power of the motor. If you need that one, record it in your observe that one and record in your manual. Otherwise just observe the uh, generator side and note down that one, because when you will be increasing the load current as it is the shunt generator, you know that the equation for that one, what is the equation for the terminal voltage? Terminal voltage will be lesser compared to the induced EMF, because when the current will be increasing, more voltage drop across the armature resistance, so that will be subtracted from the induced EMF and the rest of the voltage will be appearing across the load terminals, right? So voltage will be equal to induced EMF minus IAR, and that's the voltage drop across the armature resistance. Some voltage drop may be because of the armature reaction that we have discussed in the theory class, but that is not the part of this experiment. We just want to observe that if we increase the load, the armature current will be increasing, will be causing more voltage drop in your machine, and the terminal voltage of your machine will be reduced. So we will be changing the load by sliding this one, and that you can observe the load current is changing, and with that your load voltage is decreasing because you have more voltage drop IRA in the shunt generator, in the armature winding. The internal resistance of the winding in our lab machine for the shunt configuration is 8 ohm, and for the series machine it is less than 1 ohm. Okay, so now all the setups, all the connections have been made, and in the rest of the experiment that will be demonstrated in this video, you will observe the readings that by increasing the load current, what is the impact over the load voltage? And that is of course because of the voltage drop in the armature winding, right? So this is one is the field current, and please note that it's a shunt generator, so armature will be providing the current to the field winding as well as to the load. So armature current will be the sum of field current and the armature current, and when you are adding them together, both must be at same scale. Armature current is in ampere. If you have set the field ammeter at milliampere scale, so first of all convert it into ampere and then add with the load current to get the total armature current. So here you can see 2.27 ampere, 101.9 volt, and the field current is 104.5 milliampere, and that's the input. So now you can follow the rest of the experiment, record the things in your lab manual, and follow the instructions given in your lab manual, and plot the load characteristics of your DC shunt generator, and answer all the short questions which are given in the lab manual. So this completes the demonstration from my side. Please follow the video till the end and record observation in your manual and sketch and plot all the required characteristics as discussed in the lab manual. Thank you very much.